But meanwhile, let's focus on Newtonian physics and friction. We'll get to modern Einsteinian physics later. What is friction? Everybody right now, take your non-writing hand, press it against the table, press down fairly hard, and pull towards you. Friction is that force that you're feeling tugging in the opposite direction. That's friction. Now, somebody called me on it yesterday. They said, didn't you say friction isn't a real... It's not a real force. It's a combination of the four fundamental forces, but we're going to treat it as its own thing because it makes the math easier. Again, we're not going to dive down to the quantum level every time. So one way to think about friction is that that force that you felt resisting you tugging your hand along your table is due to the interlocking of molecular hills and valleys between a surface, your hand, and the surface, your table, and an object on the surface, your hand. So even though your table might appear smooth, if you were to zoom in, you would see that it was actually all bumpy and jagged, and your hand is not smooth either. And as they slide across each other, those bumps and ridges interlock and catch on each other and apply an opposing force, and we call that friction. That might not be right. That's one explanation of friction. There are others, and we're still trying to figure out which explanation is the best. But that's a good model, a good analogy, and it'll kind of help us understand what's going on. Here's what we do know, and this is what you want to underline. Friction resists sliding. That's the direction. A couple of days ago, we did air resistance. We said that air resistance was always in the opposite direction of motion. Friction, if you want the direction, it's going to resist the sliding. Because of that, it means it can resist motion, but it can also create motion. So for example, example 1, draw the direction of friction in each case. If we were sliding, now this document was typed in Word 95 for Mac. What year are we? It's showing its age. On mine, there's a little air gap between the floor and the box. That shouldn't be there, but I can't edit the graphic anymore. So I'm just going to do, just to show, there's no gap there, okay? Is there one on yours, on your diagram? If you pretend that ain't there. Sorry. If we pull this to the right, if it's sliding to the right, which way would friction be? This is very similar to your hand. Which way would friction be pointing? To the? So let's draw a little arrow pointing this way. And my abbreviation for friction, I usually put an F and then an FR. I don't know why I put the R, because FF would also work just fine, and for some reason I write FR. This is about the only time that I write an extra unnecessary letter, but it's a habit that I can't break. You can write FF and I'll figure out what you mean if you want to abbreviate. What about for a car speeding up? Well, if you look at this tire, it's spinning this way. Right here, where the tire is contacting the road, which way is the tire pushing? Backwards. Forces come in. What's really happening is road friction is pushing forwards. And this is why I said you can't simply say, oh, friction is in the opposite direction of motion. Here, friction is in the same direction as motion. Friction is what makes a car go forwards. That's why you can't drive on ice. See, if it was your engine or if it was just your tires that made a car go forwards, then you could drive on ice just fine. What's changed on ice? The force of friction. When you hit the brakes, what you're actually doing is you're causing the tires to apply a force in that direction against the road. Forces come in. So the tire pushes forward against the road. What does the road do? That's the force of friction. So not only is friction the force that makes the car go forwards, friction is also the force that makes the car come to a That's also why it's tough to stop in ice. If it was just your tires that were required to stop, you'd be able to stop just fine in ice. What variable has changed? The force of friction. We talked about this yesterday in class, Riley. You were away. We watched a video about friction and we used some reasoning and we said we think friction should depend on two things. The first thing it should depend on is how slippery the surface is. Or if I flip it, how sticky the surface is. It should depend on the types of surfaces that are in contact, how slippery or sticky they are in relation to each other. And this is represented by something called the coefficient of friction. That's underlined, but I'll underline it as well. The coefficient of friction has a symbol. The symbol is the Greek letter mu. This is the coefficient of friction symbol. It sort of looks like a lowercase, that's terrible. It sort of looks like a lowercase m handwritten with a long tail. Okay? This is the symbol for the coefficient of friction. This is the symbol for stickiness or slipperiness. The closer this is to 1, the stickier the objects are. The closer this is to 0, the slipperier the objects are. Okay? It doesn't have any units of its own. The coefficient of friction, mu, has no units. It's just a number. It's actually a ratio. It's a percentage, which means it's typically between 0 and 1. To give you an example of a couple, steel on ice has a coefficient of friction about 0.01. That's why skating works so well. You give yourself a push and you'll keep going. What's really slowing you down more than anything is air resistance on your body. Rubber on concrete, tires, has a coefficient of friction about 0.75. That's why we make tires out of rubber. Okay. Can you be bigger than 1? Yeah. Glue. It can handle its own mass and more than its own mass. Glue isn't really friction, it's a chemical bond, but there are situations where you're bigger than 1. Which force makes a car go forwards? Dragster tires have a coefficient of friction bigger than 1. They're really expensive, but they're really sticky. Because for a dragster, you want it to go forward as fast as possible. Yep, Aiden.
Is there a material that you think would be better than rubber on concrete for cars?
Yes, but it would be more expensive. What you're really asking is there a material in the same price range that would work that well and last that long? No. But are there better materials? Yeah. It depends what you want it for, whether you want long-lasting, good traction, or what type of weather. That's why we have snow tires, for example. But dragster tires are a good example. They have a coefficient of friction of about 2.5. But that also means that they last maybe one race and you got to replace them, which is about $10,000. So not very economical. So friction, first of all, depends on how sticky an object is. And I hope, Owen, that's kind of a Captain Obvious. Yeah, there should be a difference between ice and Velcro. Okay? Depends on one more thing. Depends on the force pushing the surfaces together. A heavier object would have more friction. Pause the video for a second. So I wrote here, it depends on the force pushing the surfaces together. And Aiden, you're right. In simpler problems, the force pushing the surfaces together is the weight, is the mg of the object. But this is not always true. I want to be able to explain why I can make it easier or harder to slide something by lifting up or pushing down on it. And yeah, it's the normal force. And so here is your final equation. This is on your sheet, but you'll probably memorize it. Friction is equal to mu times the normal force, where mu is what we call the coefficient of friction. It has no units, which is why you get newtons equals newtons. If it had units, it would change this question. And the normal force, you don't have an equation to figure out, but it's a job for a free body diagram. That also means that in almost any friction question, I'm going to be doing a free body diagram. Let's walk through some of this. Example 2. Suppose we're pulling a 6.5 kilogram mass across a rough surface. Let's say the coefficient of friction is about 0.64. Gravel. At a constant speed. Ooh, you know what? I should probably underline the constant speed phrase. What does constant speed tell me? A is 0. Oh, that also means the forces must be, I'm looking for a word that begins letter B. Let's remember that. How hard do we need to pull? What's this question asking me to find? How hard do we need to pull on something? This is a job for a free body diagram. What are the forces acting on it? Get the obvious one. Now, I know you want to go rushing to pulling forces and friction. Go systematically. Don't panic. So get the obvious one, gravity. You know what? Did they give me a picture, Ethan? Yeah. I'm going to label the picture. Technically not a free body diagram, but it'll do the same job. So gravity. Is this mass sinking into the ground like quicksand? Is it flying into you like Superman? What else must there be? The ground has to be pushing up. Same size? What else? Well, the fact that it says a rough surface means there's friction. Which way is this block sliding? To the right? So which way would friction be pointing? To the? So I always have to be careful because when you point that way, okay, were you pointing my left or whatever? Yeah. So I'm going to say friction is that way. If that was all there was, this would be moving backwards. Or sorry, this would be accelerating backwards. Oh, we're pulling. Is there a rope? What do we call the force from a rope? Is tension going to be bigger, smaller, or the same size as friction? And how do I know? Sorry? So all of you have, sorry, not all of you, you have fallen into a classic error. So you ready? What two words did I underline? So what's the acceleration as a number exactly? So that means the forces must be, I'm looking for a word that begins letter B. So I'm going to ask you again, Aiden, will tension be bigger, smaller, or the same size as friction?
Same size.
And again, and don't feel bad. Again, though, you're going to hear me say, Max, this is why I jumped on you a few days ago. You can't confuse movement with acceleration. Newton's first says this can happily keep going in a straight line at a steady speed if forces are balanced, and it will. Normally, I would say who's winning, but are forces balanced? Then it's a tie. We can say this. Friction equals tension. It's a tie. What did this question want me to find? Yeah, what did this question want me to find in the equation that I've just written down? Tension. I don't know tension. But I know another force the same size as it. Which one? So I'm going to find tension by figuring out how big this is. We have a new equation in the box. Friction is what times what? Mu times the normal force. So my next step, I'm going to replace friction with mu times the normal force. That's how big tension is. Has to be, because the forces are balanced. What's mu? I don't know. What's mu with you? What's mu? 0.64. I don't know the normal force. Oh, but look. I know another force that has to be the same size as the normal force. Which force has to be exactly the same size as the normal force? So I can say mu mg is the same size as tension. By the way, if you haven't noticed, we've cranked things up a level of difficulty because now we're doing multi-step substitutions and some deep thinking here. Do I know mu? Yep. Do I know the mass? Yep. Do I know G? Okay, now I can solve for tension. Tension is going to be 0.64 times 6.5 times 9.8, which is what? Do you get 40.8? Question, Aiden? Oh, okay. Units, it's a force. Newtons. Okay. Friction is what times what? It's mu times the normal force. I don't know the normal force. Oh, but look. I can figure it out. As you're turning the page, this one here, sorry, is a C- level of difficulty. Let's kick it up a notch. By the way, I called this tension, but we give a special name to an unknown force appearing from an outside source. We'll often just call it the applied force, and we'll often label it as F applied. And what I mean by that is, in this picture, I don't know what's pulling on the rope. It could be invisible leprechauns for all I care. It could be a winch over on that side. It could be a truck pulling. I don't care, but something is applying a force, F applied. Okay? Example 3, I like example 3, I like example 3, I like example 3. Example 3 is a nice question. Suppose we're pulling on a 6.5 kilogram mass across a rough surface, friction, with an applied force of 86 newtons. That's the mystery arrow right there. What's the acceleration of the mass? Cool. Riley, what's this question asking me to find? As soon as I said that, I saw that, I glanced. Do you see a VF or a D or a T anywhere in this question? No. Okay, you know what? I'm going to find acceleration using forces, not using last unit. Okay. Is there friction implied in this question? Yep. Is there also an applied force? Yep. So Riley, is there more than one force? This is a job for a free body diagram. Although, did they give me a picture? I'm going to label a picture. So that's how my brain leaps to the approach, okay? They said, Peniel, find A, no time, no distance, no VF. I mean, not even a VI. I can't assume we started at rest. They didn't say that. So I'm not solving for A using that way. F equals what? I'm going to solve for A using Chiana's law. Eventually, we're probably going to divide by an M. Got the plan? Is there more than one force? Free body diagram. Remember, did they say net force anywhere in this question? So I can't jump straight to F equals MA. Riley, what are the forces acting on this box? Get the obvious one. So I have mg down. Is this box sinking into the ground like quicksand? Is it flying here like Superman? So there must be a normal force pushing up, and I can safely assume that it's the same size as mg. What else? Well, I have this force coming from the right, and now I'm going to call that an applied force. Something is applying a force from the right. I really should have drawn it with an arrow like that. What else? Friction, which way? Left. Bigger, smaller, or the same size as the applied force? Well, they've told me that this mass is accelerating. So are my forces balanced? If we're accelerating to the right, is friction going to be bigger, smaller, or the same size as the applied force? I'll really exaggerate it so it catches my eye. Vertically, forces are balanced, no acceleration. Horizontally, who's winning? And good. Annika, who's the loser? Oh, Aiden, you didn't see that. I said, who's the loser? And she looked at you and shook her head. Wow. Wow. Fine, Annika. Who's the losing force? Winner minus loser equals what? MA. Riley, what did you say this question was asking me to find? Kiana, how would I get the A by itself using Kiana's law? You know what? I'm going to do it right now already. I'm going to go cross out the M and big fraction. I know that I'm going to divide that whole mess by M. Now, I know how big the applied force is as a number exactly. They told me how big. 86. Do I know how big friction? Oh, okay, here we go. So, A equals 86 minus friction is what times what? It's on your green sheet. Mu times the normal force. And that's going to be over M. What's mu? I don't know. What's mu with you? Did they tell me what mu is? 0.64? Okay. Oh, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? So I can say this. A equals 86 minus mu mg all over m. See the lengthy chain of reasoning that we've done? I'll pause though. Hopefully I haven't done anything new with you yet. We've just been going systematically, a good free body diagram and Newton's laws. Do I know mu? Do I know m? Do I know g? Do I know m? Hey, we've got everything, plug and chug. So it's going to be 86 minus 0.64. What was the mass? Oh, I'm still using the same old mass. Times 9.8 divided by 6.5. Is this a fraction? Is there more than one thing on the top? Brackets around the top or your fraction button? Is there more than one thing on the bottom? Don't need brackets around the bottom. I would encourage all of you, I would consider this here about a C or C plus level of typing in your calculator. So I would strongly encourage all of you to try typing this in. Where's your calculator? Which other class? Did you want to go get it really quickly? Do you have a mask here? Okay. It's not broken? Oh, that's amazing. Oh, sorry. You understand what? By the way, thank you for telling me because I was noticing. Don't just sit and hope I won't notice. I'll just think, okay, this kid would rather not learn than actually learn, and that just irritates me. 6.5. Hey, Mr. Dewick, how come you're not doing these in your head? This is about the level of difficulty where I run into roadblocks. Did you get 6.958? That? 6.96 units. It's an acceleration. Okay. This I would consider, in terms of level of difficulty, C+. Okay, we'll get to an A level. Alrighty. Example 4. Suppose we're pulling on a 6.5 kilogram mass across a rough surface, friction, with a force of 48 newtons. What's the acceleration? Mr. Dewitt, this looks like it's the same question that we just did. Maybe it is. Let's find out. Deegan, what does this question want me to find? First thing I would say is there a T or a D or a VF or a VI? Because that's what we did to find acceleration in the previous unit. No, I'm going to solve for acceleration using Kiana's law. We're going to divide by M eventually using F net equals MA. Okay, this is the job for a free body diagram. How do I know? I got friction. I got an applied force coming from off the page. More than one force. What are the forces acting on this, Deegan? Get the obvious one. What else? Is it sinking into the ground like quicksand? Is it flying you like Superman? So there has to be a normal force canceling out gravity. Otherwise, it would be accelerating vertically. Mr. Dewick, why can't I just assume that the normal force equals mg? Because I'm giving you simple questions right now. Later on in this lesson, we'll ask, what if the normal force doesn't equal mg? Okay. What else? Oh, there's an applied force, Deegan, pulling to the right. F applied. 48 newtons. What else? Yes. I think to your left as well. Call me silly, but I'm pretty sure it's also your left. Yes. So you could just say to the left. Right? Right? That was good. You find it? Sorry? Okay, check your bag. Otherwise, I'll give you a loaner. Who's winning, Deegan? Who's losing? You say friction? And that's going to equal... Hey, what are we trying to find? I did Kiana's law right away. By the way, look up. Don't write this down. As far as I'm concerned, I could also give you the mass and friction and ask you to get F applied by itself. How would you get F applied by itself? I would say, how hard do you need to pull? How would you get the F applied by itself? How would you move the friction over? Add it. Okay. As far as I'm concerned, and we'll do one later on, I could even ask you to solve for mu to get the coefficient of friction by itself. And that's one of the reasons I've taught you all this formula manipulation, is that once I show you one method, to me then it's fair game to say you can get whatever you want by itself. I can ask for anything. But for now, we're using Kiana's law. So I'm going to have A equals F applied, which was 48, minus. Do I know friction, Deegan? Hey, no. Oh, but I have a new equation for friction. Friction is what times what? Mu times the normal force. All over m. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? Good. So I think I can go like this. 48 minus mu mg all over m. Aiden, by the way, hopefully you're also now seeing why I kept jumping on you whenever you said 9.8, because a common mistake that kids make is they forget to put the m in with the mg. They go mu g because, oh, that looks like a force. No. Okay. 48 minus 0.64 times 6.5 times 9.8. Is this a fraction? Is there more than one thing on the top? Brackets or your fraction button. You get 1.11261, and if you didn't get that, now is your time. Don't clear your calculator. Just raise your hand and I'll come look over your shoulder if you didn't get that. Because part of this is also, I gotta be able to type this into my calculator, okay? You get that okay? Good. What if you solve for A and you got a negative answer? Now, here's what it would mean. You picked the wrong winner. Now, it would catch your eye. What? Negative? So quickly redo your question. Make your winners your losers your winners. In fact, here's how I would do it. I would be so lazy. Don't write this down. I would say, oh, that was a winner. That was a loser. I wouldn't even rewrite everything. And I would quickly, oh, That's a winner. I would quickly do that and then just retype on my calculator. So there's a bit of a built-in error check here if you're finding an acceleration. If you get a negative answer, don't ignore the negative. That's telling you something. You probably picked the wrong winner. So for example, if I've been pulling with 30 newtons, I'll bet you it's not overcoming friction. What that would tell you is this box is slowing down, not speeding up. Okay, doable. Next page. Example 5. A student gives an old shopping cart a big push on a flat, rough surface. Underline the word rough. Whenever I say rough surface, which force am I telling you to include in this question? Friction. Okay. Which of the following is the best force diagram, free body diagram, for the cart after the student has released it? And there's 4 to pick from. Now, I don't have a shopping cart. Let me just pause the video. Who says, Mr. Dewick, A is the correct free body diagram? A. 1, 2, 3. Ooh, we could have a good controversy here. Who says B? Obviously B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who says C? 1. Who says D? 1, 2. This is about as big a split as we've had in one of the, and this is why I like this question conceptually, because it is a difficult concept to wrap your brain around. You don't get to re-vote. That's not how elections work. Once you put your ballot in, you can't go fishing your hand in and pulling it back out. You'll get arrested. It's a nice try. Convince me. You can either attack someone else's answer as theirs must be wrong, or you can convince me that your answer must be right. Convince me. Yeah. What are you defending or attacking?
Defending B.
B?
No. Because your person's pushing the shopping cart, so there's a force going through.
Oh, was I shaking my head? Sorry. Yeah. Well, let's see. Okay. In D, which way do you have an unbalanced force pointing which way? To the. So which way must D be accelerating? To the. Okay, we'll try this again, and this time people are going to say a word out loud. In D, which way do you have an unbalanced force pointing? To the. Which way from Newton's first law, which way must D be accelerating? To the. In D, which way do you have an unbalanced force pointing? To the right. So which way must D be accelerating? Right. To the right. This would have to be speeding up. Yes, that's Newton's first. Was it speeding up once it left my hand? Sorry, those of you that voted D. What about in C? In C, the forces are, I'm looking for a word that begins letter B, which means what would its acceleration be exactly as a number? That would be going in a straight line at a steady speed, neither speeding up nor slowing down. What's what you saw, neither speeding up nor slowing down? In B, forces are, I'm looking for a word that begins letter B. That would be going in a straight line at a steady speed, neither speeding up nor slowing down. In A, what direction is your unbalanced force? To the left. So which way will A accelerate? To the left, which means if it's moving to the right but accelerating to the left, how would that manifest itself? It would No, this is why I keep telling you, this is not easy stuff you wrap your brain around. I know this question is coming up, and I always get a 4-way split, always on this question. And hopefully now, those of you that didn't vote A are going, when in doubt, imagine the free body, or look at the free body diagram. Newton's laws. In fact, which one of Newton's laws did we use here the most? Newton's what? We used first. If forces are balanced, you're not accelerating. If forces are not balanced, you're accelerating in the direction of the unbalanced force. Objects at rest tend to remain at rest. Objects in motion tend to remain in motion. Newton's first, very powerful. Okay. Warning. If you sign up for Physics 12, I'll get you on this again. In a different way, but I'll get you. Oh, if you couldn't, by the way, if you couldn't remember that we used Newton's first, because was it first or third? Because somebody said third, which suggests to me they weren't quite sure. You could always have said unbalanced force will cause the acceleration. Only A has an unbalanced force to the left. And I would give you full credit. So if you paraphrase Newton's first law as a conceptual question, I will give you full marks. But if you knew for certain it was Newton's first, then I'm fine if you just write that down, drop the mic, and walk off. Example 6. A force of 12 newtons is required to keep a mass accelerating at 0.8 meters per second squared. What's the coefficient of friction between the mass and the floor? What's this question asking me to find? Hey, what's mu? I don't know. What's mu with you? It's asking me to get the mu by itself. I'm going to start out, George, the same way. There's clearly more than one force in this question. We are talking about friction since they want the coefficient of friction. This is a job for a free body diagram. Although, did they give me a picture? I'm going to label the picture. What are the forces acting on this, George? Get the obvious one. What else? What do we call the support? Thank you. I'm glad you have an FN clue. What else? Well, they put the 12 there, and there's already the arrow there. I'll just write a little app underneath the F. I often write something on a typewritten force so that in pencil or in ink, it's a different color, and I'll notice it, not to forget it, because sometimes you just ignore it because we're tired, right? What else? Friction. And I know friction must be losing because they told me this is accelerating to the right. Well, they told me it's accelerating. Okay. Who's winning? More specific, in this question, who's winning? F applied. Who's losing? That equals MA. Not dividing by M because we're not being asked to find A. In fact, where is the coefficient of friction hidden? Inside there. So my next step is I would replace friction with friction from your green sheet is what times what? That's what I'm going to get by itself. Okay. Yeah. What don't I like right now? What's right in front of the mu that makes me go, yeah? A minus? Oh, swappy dance? Yeah. Hey. So you're saying I can move that to that side, the whole thing, mu Fn, and I can move this to in its place, and I'll get F applied minus MA equals mu Fn. I think that's much prettier. Oh, how would I get the mu by itself? What's the Fn doing to the mu? Multiply. So, problem. I don't know the normal force. Oh, but look. I don't know the force. So, on this line, because I'm lazy but organized, I'm going to go like this and move the Fn down to there. But on my next line, I'm going to write, I guess mu equals F applied minus MA over, what can I write instead of the normal force? mg. Mr. Duick, why can't I just replace the normal force with mg right away? Because I'm giving you easy examples so far. By the way, what's going to happen coming down the road is there will be extra vertical forces, and so you'll have to really puzzle out how big the normal force has to be. It won't be mg. Just haven't got there yet. Okay. Need to give myself a bit more room here. I love digital ink. How big was F applied, George? I've scrolled down. Oh, 12? Yes. Minus 5. What was A? divided by 5 times 9.8. Hopefully you'll get a decimal between 0 and 1 because that's what the majority of mu's are. Unless I've made up bad numbers, which happens sometimes, but is this a fraction? Yes. Is there more than one thing on the top? Yeah. Is there more than one thing on the bottom? Yeah, brackets are on the bottom. Yeah, this one in your head, Mr. Well, it's going to be 5 times 0.8 is 4, so it's going to be 12 take away 4, which is 8. It's going to be 8 over 49. 8 over 50 would be 4 over 25. What do you get? 0.08, 0.09? Or am I way off? 0.16? Oh, I was way off. Is it 0.16? People even?
Well, 163.
0.163? Units. Is this a force? So, newtons is a bad guess. Units, and your hint is, it's a trick question.
No units.
No units. This is one of the few things, it's, by the way, because it's actually newtons divided by newtons. The newtons would cancel. Nothing left behind. Is that big? That'd be pretty slippery. That would be like the mud at the bottom of a mud puddle, or if you've ever walked on and hit just a little patch of wet dirt where your foot just starts to slide a tiny bit. So not ice, but slippery. Wouldn't be comfy to walk on. Put your pencils down, look up. So friction is mu, stickiness or slipperiness, times the normal force, how hard the ground has to push up. Okay? What's your homework? Take home quiz. You can try number 1, number 2, 3, and 4. Sometimes I haven't given you a diagram. That's when I would draw the free body diagram. You might be able to show your work on this sheet, or you might do it on a separate piece of paper. I don't care. 5 is good. Sorry, let me do this. I'm curious to see who can figure out number 6 and number 7. Those are so easy that they're tough. 9 is good. 10 is good. Mr. Dick, why don't you just say to every question, because I'm never quite sure which ones I'm skipping or which ones I'm not. Okay? It's 9:52. Can I mark the take-home quiz at 10:30? Okay?